Hello, guys. Before we're gonna move into a new topic, which is procedures. So when I say procedures, I'm talking about methods or functions. It depends on the type of the language that you first used. Let's say if your first language is Java, you know them as methods, and if your first language is C, you know them as functions. If your first language, I'm sorry, is C, you know them as a function. If your first language is Pascal, you know them as a procedure. So it doesn't matter. You can call them procedures, functions, subroutines. So they all different names for same thing. So all of them, they require a stack. So in order to under procedures, we need to understand what's a stack, okay? But before I move on into the topic, I just very briefly, I want to talk about quiz 4. So I get a lot of feedback from many of you, and there was like a common a concern that the number of questions were more than the assigned time. So I decided to grade your best 2 questions out of 4 and assign that as your grade. Okay, so whatever you get out of the 4, the best 2, and then I assign the grade for those 2s, the total of those 2 questions as your quiz 4 grade. And I hope that's going to be fair for everyone, okay? Because I thought about making them 3, and then I thought 3 maybe is not fair again, so I just went with the 2 questions, all right? So the TA will release them either today or tomorrow. We already graded them, but I was just thinking about talking to my TA and listen to the data that I get from you guys. So I just thought that the best way is to go half of the quiz is going to be graded, the best half of the quiz, okay? For quiz 5, hopefully you had a good experience today. I tried my best to make it also something doable within the time. I have 5 to 8 students who really had some technical issues. I apologize for those, but it's really beyond my control. Some of those, they really trying to make it really hard on us because they keep saying we don't have cameras. I don't know whether that is true or not. It could be true. So if it's true, I apologize. But I cannot imagine someone living in this time that they do not really have a camera. If you really don't have, then you really need to figure it out because the world are going to be virtual and you need your camera either way for this class or maybe in your future meeting or maybe the future jobs are going to be online and you need to have your camera anyway. But even with that, maybe you have some financial problems. Maybe you're coming from a family that cannot provide. I truly understand, okay? I do understand. If that is the case, then I am sorry. But I believe that for some, I might be wrong, I apologize, but I believe like for some, it was just really trying to make it hard on us that I don't have a camera. My camera doesn't work. My computer have this issue. So we are going online. So you need your camera, you need your microphone, you need your laptop. So these are things that you need. I know that these things cannot be provided over time. So that's why I asked the TA for those who had technical issue to just be as flexible as possible because it is not planned. We did not like really prepare you for the online. So even if you're trying to make it hard on us, I tried my best to really accept that is the fact and we try to accommodate you. So what I was hoping that you just please try to understand that we have limits as well. So when we give you more time to do something, when we reduce our quality of work, we're just trying to accommodate you. But every time we do something, you should also try to help us as well. It's a two-way kind of help, guys. It's not like only us, it's our problem. It is everybody's challenge, right? So just to do the online. So we will see. As I promised you, I didn't make any decision for quiz 4 until I saw the data because I'm a scientist and I believe on data. Once I see the data, I can make up my mind. And again, for quiz 5, I will look at the data, see the performance. If I see something that is really concerning, you don't need to worry. I will take care of it, okay? So with that, if you have any questions, I will have my office hours today at 4. So please try to show up and share your concerns, your feedback. And if I am mistaken, for those who I consider that they are just trying to make problems when saying, I don't have time, I don't have camera, I apologize, but please come during the office hours just in case if you have a point that you need to make. Okay, so with that, I will try to go ahead and talk about procedures. But as I said, if we want to understand a procedure, we must understand the stack. So without the stack, we cannot understand how a method works. Okay, so let's get started. All right. So the first thing that we're going to look at today is we're going to look at the stack. All right. So when we look at the stack, we actually want to try to explain what is or what are the operation in the stack. And then if we got the time today, we're going to define how to define and use a procedure. And then the other goal is to look into the external libraries. This is straightforward. Okay, but this part is very much important for this part, and this part is actually going to be kind of not directly related. Okay, so we're going to focus on these two. All right, so let's first look at why stack, why we need a stack. So as I said, we can call it a procedure, we can call it a function, we can call it a method, you can call it a subroutines, it doesn't matter. Okay, so this is like a fundamental, right, features for all languages, right, guys? So we need it. Okay, so we need it for one reason. Okay, so code reuse. So without a function, you're going to end up really copy pasting the same code multiple times because you don't have a specific function that you can call every time you need that functionality. So we need it for code reuse. So we need our procedures, right? We must have them. All right. So you might say, no, but there is a Fortran. It's a language that doesn't really require procedures. Yes, that is the only language that really doesn't require procedure. It runs things without a stack, which is very weird. I'm not going to spend the time in talking about Fortran, but it is a language that really works without a stack. Because if you need a procedure, then you must have a stack. If you're going to say, I will use the procedure without the stack, that is not something common, especially for C-based languages like Java, Python, all of these languages, they require that you have to have a stack. So that is the first thing. So that's the code reuse, right? So what is the second thing that we need procedures? It's easy debugging, right? Can you think about how debugging becomes easy if we use procedures? Of course, because you can determine whether the problem in this function or in that function. So if this is your method or function 1, this is your function 2, and this is your function 3. So that way you're gonna you know that the problem comes from this method, right? So you don't need to waste the time looking onto the other, looking at the two different methods, so maybe 5, maybe 20, who knows? So you're gonna focus the debugging just for this particular function. But if your code is just one piece and the whole code is written there, debugging becomes really hard, especially for large systems, okay? So we're gonna say obstruction. So what do I mean by obstruction? All right, so obstruction is something that is very important. It applies, right, for everything we do in computer science, all right? And this is a term inherited from mathematics. So what is an obstruction? So what the method obstruct? It obstruct a specific thing, because remember, when we write a program, we are writing a program to solve a problem. So when you look at the problem domain right here, wherever the domain of that problem is, when you look at the problem has its own nature, right? So it has maybe a process, right? So if the problem is that you need to compute or you need to program, it has a process. So you have to do step 1, then step 2, then step 3. So when you look at the problem and you try to understand the process or the steps of the way they manually do this problem, because we want to transform this problem into an automation, right? So if that is the case, then what you're trying to do right here, you're trying to look at the problem and you need to map this problem to what? To the computer domain, okay? So you want to do this and map it to the computer domain, right? So you can think about this step right here as a procedure, this step as another procedure, and these procedures, they interact together to achieve an ultimate goal, right? Which is solving this problem, all right? Let's say whatever that problem is. Okay, so when you think as a programmer and someone needs to automate something, you have to have an abstraction in your mind, because you want to map the problem from the problem domain to the solution domain. So the computer domain, that is what we call the solution domain, okay? So they talk in the problem domain, you want to map this to the computer domain. How? Okay, so that is something that we need to have an abstraction. So procedures helps you. And you also guys have another type of abstractions, which is OOP. So in OOP, you don't think procedurally. In OOP, you think using what? Using objects instead of using procedures. So the object is, the procedure is part of the object. So that way, this is another level of abstraction. So that's what abstraction is all about. So our abstraction right here is at the procedural level, not as the OOP level, okay? And then the other part is we're gonna talk about is they allow us to refer to some piece of code by a name, right? So that's a great, that is the whole idea of a procedure. So you have a name right here. And not only that, you can pass parameters. So with like varieties of values, and that's the great thing. So if you're gonna say, okay, I don't need a procedure, so I'm just gonna write one piece of code, okay? And then I will write everything in here. Every time I need it, that is my code one, I copy and paste it again in the other part of the program. So now I'm saying copy the code one to this part, right? So I don't need a function. So I said, I'm okay with repeating the code multiple times. But when you go and you copy it here, maybe you're now processing a different value, right? That's, of course, is going to be A and B, but A and B here, they're going to be with a different value. They're not going to be with the same value. If they are, then you have a point. But if they're not, then you have to change a lot of things. But the good thing about a function, you're just going to pass the parameters based on the value you have, and then they're going to return you, they can return to you the result, right? Let me see if I can erase those. I'm sorry, I'm a little bit slow. I'm learning the technology right here. Okay, so that is the whole idea right here. Is just to show you why a function or why a method. Okay, so so all you need to know when you write a method is how many arguments, right, that you need to pass. Is that correct, guys? And then you need the type of argument, integer, string, char, what exactly that you need to pass. Okay, and then what the subroutine returns. That's very important. Okay, so the subroutine or the procedure needs to return something. Correct, guys? And then you need what the subroutine computes. It's not necessary. I don't care how the subroutine is going to compute it. All I know that is going to do the average. How do they compute the average? I don't care. Just give me the name, and I need to do the average for number of parameters. I'm just going to pass them. You give me back the result. That's what the procedure is all about. Okay, kind of why we need a procedure. Is it clear? Okay. What happens in a subroutine call? That is something that we need to focus on, right? So this is very important. Okay, so the whole idea right here, let's say if we have this method, pick the minimum, right? So this is the name, and these are the arguments that we have right here, right? And this is how this method computes this particular problem, which is returning the minimum value, and this is the return message, right? So when you call this from here, how that is going to be implemented in hardware, in terms of hardware? That's what this class is all about, right? We need to understand that. Okay, so when a subroutine call is executed, then the arguments need to be what? Evaluated to values, right? So if you call them, let's say from here, and let's say if you call them from here, let's say pick, okay, minimum, and let me say 5, 6, and 7, right? So this is what we are passing. So we need to assign those 5 to X and to Y and to Z, right? So these are, we called it from the caller, right? Let's say if this is the main function. And from the main function, you are calling this. So this is known in the main function as values, but you need to go to a procedure, which is another function. That's function 1, that's function 2, procedure 1, procedure 2. And then you need to pass those values. So where those X, Y, and Z exist, where do they, where can you find, I mean, where is the location? Where are the locations of those? Are they within the main? Are they somewhere else? Are they in the global data? I don't know, but I know these are variables. And they have type as well, which is integer. We know it's 32-bit, and we know it's signed integer. Okay, so this is something important. So we need to assign those values to those space or those arguments, right? Then we need to do the control flow. So how to go from here to there? It's not magic, right? So now we know that we have a function called jump, right? So this is a jump function. So there must be a jump function that's going to go from this space to that space. So it seems that the procedure name is a label, right, guys? So it's a very well-known label, right? So it is label right here. We need to jump to this label in the memory. So it seems the dot code, it has the main function and it has the pick function. So these are two types of memory. So if you want to jump from here to there somewhere, if you are in the main and you want to jump here, so you need the jump statement. So that's what we're going to do. But how? How are we going to do that jump? So this is what you're going to cover today. Okay? And once a return statement has been encountered, we are done, right, with the subroutine, and we need to return. So if we are right here and we say return, and then we say return to where? Maybe in this case, return the minimum value, but to whom? So we called from the main. How return knows where main is? And how the control right here is going to be given back. That is the whole idea, right? How the control is going to be given back to the main. When we jump from here, what happened? Can you think about it? What controls .code memory? It is the instruction pointer, if you remember, right? So you're changing the instruction pointer from pointing here to go and point here. So now I want to change the instruction pointer to go and point into the next instruction, because this is done. We executed it and we returned the value. Okay? So we're going to learn how that actually happens. So in order to understand all of these like points that I tried to talk about right here, we're going to see the stack, because the stack is going to help us save those temporary or assign these values to their related space in the memory, and is going to help us also remember who calls what. Okay, so that's going to help us in returning as well. All right, so it's going to be very much interesting. So before we go into the stack, I just want to remind you that this stack is not the stack that you learned in data structure. The stack you learned in the data structure is just a way of organizing memory in a specific way, first in, last out, okay? Or like last in, first out. Do you see what I'm talking about? That's how the stack works. So for you, you learn that as a data structure. What we're talking about here is the same principle, the same procedure, but this is a hardware implementation of the stack, okay? So this is not software. All right, so just gonna look at the stack operation right here. So just to know that at the runtime, right, what those stack operations are. So you remember, right, we have push and we have pop, okay? And we have like how push and pop actually gonna affect the stack, all right? And then we're gonna look at some examples when you're gonna use the stack to save some data. Okay, and we're going to look at some related instructions. All right, so when I say the stack, I'm talking about memory. As I said, I promise you, right? So this is not something that software or whatever you learn in data structure. This is a hardware stack. So this is your memory. Part of your memory is assigned as a stack. If you go to the Visual Studio, you will see that, okay? If you can go to the Visual Studio and you run your Visual Studio, and you copy paste the stack pointer, because you have the stack pointer register. Copy the value in the stack pointer register and paste it in the memory search box. It's going to take you to the stack. So it's a memory, okay? But that memory is being organized in a specific way. I will try to run the Visual Studio and show you that as well, okay? But let me first look at it. It's a memory. And the good thing about this memory, it is really designed in a very specific way. This is very critical, guys, okay? So if this memory, if we look at the like data memory usually starts from low to high, right? So we have like address 1, address 2, address 3, sorry, address 1, address 4. So it goes in this way. That's how it grows. It depends on how you lay out the memory. You might also start counting 1, 2, 3, 4. So there is no problem with that, but it goes in a specific direction. lower address to a higher, to a higher, to a higher. Okay? But the stack does not. This is the stack memory. Okay? The stack goes the other way around. It starts at a high address. So start from 4, and it's going to grow in this way, 3, and then 2, and then 1 until the end of the memory. So this is how the stack grows. It grows in the opposite of what? The opposite of the main memory. Keep this in mind. This is #1 fact. If you know it, it's going to make things way easier. Okay? So this is the bottom of the stack. This is the top of the stack. So if you're going to keep pushing data, then the stack is going to grow in this way. It's going to grow from a higher address to a lower address. Normal memory, they grow from a lower address, like 1, 2, to the higher address, okay? So if you imagine the whole memory right here, this is like a whole memory, not only the stack. And we know the address number here if we go in this direction, right? So we're going to say this is 00000001, and we have here 00000002, and we have here 00000003. Okay, so this is how the memory grows, the dot data memory. This is the dot data memory. So you're gonna have 5 in here, 6, 7, I don't know, or maybe another 5 in this memory. If you have a stack, the stack must be created in this way. So maybe it's gonna be right here. This is the dot stack, and the stack is gonna grow in this way. Okay, so if you insert something, if you insert 2, it's gonna go here, 3 is gonna go here, 1 is gonna go here. So that is the top of the stack. Okay, so now my top of the stack is this. So why the top of the stack keep changing? Because we have stack pointer. So the stack pointer goes down, grows, and shrinks based on push or pop. Okay, we're gonna talk about that in more details. Okay. So if that is clear, then we're gonna look into the runtime, and this is like a concept that you guys already know, right? So you need to understand that this is the top, this is the bottom, and every time you get it, depends on how you lay it out, right? Every time you insert something, you're moving to the top. So what moves right here, this bottom and top, they all controlled by what? Keep that in mind, the stack pointer register, okay? So the stack pointer always points at the top. So it seems the top was here, and now the top is right there. Okay, so that's the last in, first out kind of principle that you already learned. But this is a hardware, keep that in mind. Okay, so we're gonna look into a real stack. So this is a memory, right guys? So this memory here we have F0, and since memory is a 4 bytes, 32-bit register, if you add 4 to this number, F0, you're getting F4. If you add 4 to this, you're getting F8. If you add 8 to 4, you're gonna get 12, which is C. If you add 4 to this, now you're going to get 0, 0, right? If you just add them. So it seems that the memory grows in this way. That is the normal memory, not the stack memory. We're talking about the stack memory. The stack memory grows in the opposite way. So now it points right here. Okay, so that's what we say, the stack pointer. So the stack pointer points right here at the top of the stack. If you push another value, then the stack pointer is going to go right here. So do you see that the stack pointer grows in the opposite way? It goes from high address to low. You subtract 4, you get 8. You subtract 4, you get 4. You subtract 4, you get 0. So it grows in this way. So every time you push a value, you in fact subtracting something from the ESP. Don't you agree? You subtract something from the ESP. All right? We're going to talk about that. So just keep that the stack pointer is the ESP, the one that we are using in this class. We are not going to use the SS, okay? Because the SS is going to be used in the 16-bit. We are not using the 16-bit. All right? So this is something that I already talked about. That's the gross down, okay, to the lower address. And that should be very much clear right here. Okay, so now we want to see now how the stack pointer is going to grow or is going to shrink. Okay, so if you look at this part right here, that's where the stack pointer is right now. So if we use push, these are the push type of push instructions. You can use registers, or you can use immediates, that's fine. Okay, you can use memories as well, but be careful when you use memory, make sure it's 16 or 32-bit. Okay, so if you look at this part now, when we push, are we gonna add or subtract? Can you think about it? Are we moving from high to higher? Then we add, but we are moving from high to low, right? So we should subtract. So we subtract the stack pointer first, and then we copy the value. If you do not subtract, then you might overwrite this value. So first you have to subtract, you got it here, and then now you push the value. So that way you're not gonna affect the other value right here. So if you do this more times, I mean multiple times, then the stack pointer now, that is the top of the stack. So that's how the stack grows. So the stack grows by subtraction, right? Every time we get down, we subtract. Can you tell me by how much we subtract the ASP? What is the amount? So you might already thought about it, right? We subtract 4 because the memory is a 32-bit, right? If we grow up, we add 4. That's what we did. Plus 0 plus 4, we get 4. 4 plus 4, we get 8. 8 plus 4, we get 12, which is C, and so on and so forth. So we grow by 4. That's how the memory goes, right? 32-bit address size. We don't care about what this address is pointing at, byte or a word or a new word, it doesn't matter. But an address is 4 byte always, regardless of the size of the memory. So we're going to subtract 4, and then we assign the value, like the one right here. Then we're going to subtract another 4, create the space first, and then we assign the other value. Subtract 4, and then we assign the other value. Okay, so that's what you see right here. So every time we subtract 4 from the stack pointer. Okay, so now if you want to look at the pop, which is very interesting, similar, but when you pop right here, you pop a register, right? Interesting, or memory. But when you pop, usually you pop things from where? Right? You pop them from the stack, right? So this is something that I would like you to keep in mind. This always confuses my students. So when we say push right here, guys, we say push 5. What is the source? Of course, obvious, 5. Where is the destination? It's not explicit, but it's implicit, right? Because push is gonna take this value and send it where? It's gonna go here to the stack, and it knows that the stack pointer is pointing at something. I don't know what it is. So push is gonna do what? Subtract 4 first, and then it's gonna push the 5. So that way we are not gonna overwrite whatever the value here. If we have another push right here, if we have another push right here and we have 10, we have to subtract 4 because we're growing downward, and then we're gonna have what now? 10, right? So now what if we know that stack pointer now points here, right? What if we wanna say pop? Pop is gonna copy the top of the stack. So it's gonna copy this, so that is the source, right? Where is the destination? It could be a register. Let's say if I wanna move that to a register, let's say AL, okay? So this 10 is gonna go to AL. So where is the source? AL is not the source here. The stack is the source. It's gonna copy the top of the stack, put it in AL, and it's gonna now point at the next. So now the top of the stack is 5. So the pop is gonna do what? Copy, and then what? Add 4. Okay? The push is the other way around. It's gonna subtract 4 first, and then what? Copy. So this is copy first and add 4. Do you see it, guys? I hope that is clear. All right. I know you maybe know it, but this is 1 and this is 2. But I want to make sure that I'm not making the wrong assumption. So that's what the pop. So when you see the value here, this is the storage, because you're going to get this and you're going to store it right there. Okay, guys? So this is what you're going to see next. So if your stack pointer is right here, you're going to copy 2. So let's say if you say pop right here, and you're going to say pop to AX. Okay, let's just be safe. EAX. Okay, so what we're going to do, we know we have first to do what? Copy the value. You see? So we're going to copy the value. So we're going to get 2 to EAX, right? So EAX is going to have 0, 0, 0, 0, 0, 0, 0, 2. Okay, and then we're going to do what? We're going to add. So the stack pointer now is going to go right here. If we have another pop right here, which is EBX, then we're going to copy 0, 0, 0, 0, 0, 0, 0, 1 to where? To EPX. Okay, and then once we copy that, then we're going to add. So it's going to point right here. So it's going to go in this way. Do you see it? So this happens here. We copy the value to EAX, and then we add. So when you see it clean as here, I don't want to confuse you. The value are not going to go away. They're going to stay there. We're just going to increase the stack pointer. I will show you that when I run the Visual Studio. Okay? So the value is not going to disappear. It's not going to delete, because deleting is very expensive, by the way. Okay, so it's just gonna take the stack pointer to here. So what happens to this value? We don't care, it's garbage. So if you pop another value after you, if you push after pop, then this value is gonna be what? Is gonna be written or overwritten by the new value. Okay, guys, kind of clear? Okay. So this is the stack application. If you want to look at the stack applications, these are like multiple type of stack application. All right, we can use it as save area for registers, right? But that's not what is really meant to create the stack. The stack created to really store one specific thing, which is call and return. I will explain that in a minute. Okay, and that is one thing you can do anyway. That helps, and we can save on the current subroutine return address. That is the key idea. This is expected because it's a memory. We can store in the data. It's not an issue. But for the functions, we need the stack. And you might think about it, why a stack? Why not storing the return call in the data? Why we have to use the stack? If you think about it, function 1 calls function 2, and function 2 calls function 3, and function 3 calls function 4. And then at the end, function 4 has to return what has been called for, right? And so on and so forth, right? So you need to go from a higher memory to a lower, and then you go from what? A lower memory to a higher, right? Because the memories, in the memory, F1 has to be first, F2 has to be second, F3 has to be third, and so on. So in fact, you are going from what? Lower to higher, but the return is gonna go what? Higher to lower. So that's why you need a stack as a way to solve this problem. Okay. So this is mainly an arguments. You can also call it to push some arguments in there to save the arguments. That's what happened when we say pick. Remember when we use the pick minimum value and we say 5, 6, 7, and so on. So you can use this stack to hold those values as well. Okay, we're gonna cover all of these. It's fun. This is the best time to learn the stack. Okay, so it's just a temporary storage for local variables as well. That is a key thing, another key thing in here. It is to do the return and to store the local variables. I'm not saying these are not important, they are, but these are the key things, okay? All right, so now we're gonna look into using push and pop, just like simple examples right here, all right? So if you look at this example right here, remember when we did the nested loop, right? When we did the nested loop back in the days, we don't know the stack. So we created a memory, we called it temp, right? And we say D word, right? And we assign it a question mark, right? And right here, what we did back in the days, we said what? Move to temp, okay? To temp, what? ECX. So we use temporary as a temp as a variable in the data to hold the value of the ECX. We don't need to do that anymore because we know the stack now. So we're gonna say push ECX, right? And now we update the value of ECX. That's the ECX for the inner loop. Remember that? So when we are out of the inner loop, we don't need to use another move to ECX temp, right? That's what we did last time. We're just gonna say pop, assuming that the stack is not gonna change, and that's like a big assumption. All right, but this is one way you can use the stack. All right, that is important, just to show you that. Okay, I'll play with this with the Visual Studio, so that way it's gonna make a lot of sense, but I'm just gonna lay down the theoretical part first, and then we're gonna play with that. You're gonna play with it in the lab, and then we're gonna play with it, if not this week, it's gonna be the following week as well. All right, so here we're gonna use push and pop, right, to save or restore registers. All right, this is very important. So this is very critical. All right, so let's say right here, if we have variables right here, this is the array, right? And I have some important values right here. So I have the offset of the array, right? So ESI has the address. And I have the length of this array stored in what? ECX. Okay, and I have the type of this array assigned to what? EBX. And I want to call this function. Remember, when you call this function, are those registers Specific purpose or general purpose registers? You guessed it right, they are general purpose. So how do you guarantee when you go to this function is not going to change those values? We don't know. So to better be safe than sorry, we have to push those values in the stack and go to this method. If this method actually changes the values, we don't care, but we're going to make one thing clear. When we return from that, we want to return the stack. We want to return the values in the stack back to those registers to the state before we call the method. So the stack is going to help you on that, okay? So this is very important. So that's what we're going to do. Okay, so we're going to push ESI, ECX, and EBX. We push the register, so that way, what is the top of the stack? So the top of the stack is going to be what right here? If this is your stack and your stack is going to grow, that's your ESP, please always draw it in this way. Always subtract 4, because you don't know what's in here, and then we're going to have ESI, right? And then subtract 4, and then have ECX, and subtract 4, and we're going to have EBX. So what's the top of the stack now? The stack pointer is pointing at EBX, okay? So now we have our own normal value. We say assign this, assign this, assign this, and then we are calling the dump. After we go to the dump, it might changes those values. We don't care. So when we return from there, we say pop what? EBX. So we're going to get the value because that is the source. This is the destination, okay? So we're going to take the source, the value right here, let's say just 15, I don't know. We're going to take this 15 back to EBX. The reason we say EBX because that's the top of the stack. But when we push them, the first in was last out, right? That is the first in is going to be last out. Or I can read it in this way, last in, first out. Okay, you can read it in any way. So you're going to pop up them. So that's the whole idea of the stack. So this is what I try to explain right here. Okay, so that's the restore. This is the save. This is the restore. Okay, so you can use them to solve type of similar problems. Okay, this is a very interesting example. This is another example when we're going to look into how to use the stack. This is not the focus of this class. The focus of this class is to understand the relationship between the stack and a procedure. But in order to do that, we need to understand push and pop and how the stack pointer moves. And then we're going to go to the return, and that's going to be the key thing. Okay, so in this problem, it's straightforward. We are trying to do one simple thing. We want to reverse Abraham Lincoln. So this is a dot data memory, right, guys? If it's a dot data memory, and if you imagine that this data memory, just imagine, okay, and it grows from 0 to n. That's the addresses, right? And if you store this, we know that is going to be little endians, right? So we're just going to go and take the first byte. Remember, this is a byte, so we start left to right. You should not mix it up. So we're going to say what? We're going to say A, and then B, and then R, and then A, and then H, and then A, and then M, right? So this is a prime. And then we're going to do a space, white space, and then we're going to go to the rest, right? Until we get to the top right here. I'm sorry, not the best way I want to draw, but this is going to be the \0. So that's when you're going to store the end of the string, right? So what if we want to reverse this name? We just want to make it this way. We're just going to make it right here, NLOCNIL, and then we're going to have a space, and then we're going to go to MAHARBM. We're just going to reverse it in this way. Can we do that? This program is going to do it. Okay, so we have a memory, and you remember the $sign is going to tell you the end of the memory, right? That's the last thing you stored, which is going to be in our case here. So the reason we say -1 in here, because we don't need to reverse the end of the string, right? This is something we should leave in there. We just want to reverse the characters that we have in there. Is that clear, guys? So that's why we say the size here is everything but this, because we don't need this. So that's why you see the -1. And then here we move the name size, okay? That is the length of this string to ECX. We move 0 to ESI, and we use move ZX right here. Why is that? Because we want to move the name, right? And the name right here, the name is a byte, right? And we need to move it to EAX. So since it's a byte and we need to move it to EAX, we have to use the ZX, right, to extend the byte into another 3 bytes. Do you see what I'm talking about, guys? So we have a byte, but we have another 3 bytes that we need to worry about, right? So here we're going to have A, but we want to move this to EAX. So we have to extend it with 0, 0, 0, 0, 0, 0. So that way we are not going to end up having mismatching. Okay, so you might wonder, why don't we just have AL? Why don't we just move this to AL? Try that, please. Okay, is it a problem if we push an AL? Try that at home, okay? Until I do that myself when I run the Visual Studio. So here we moved it to a 4 bytes and then we pushed EAX. So when we do that, we know that is my stack right here. And remember, please do this all the time. That's your stack. So your stack pointer is pointing at something. That is the top. Never copy here. Always subtract 4, remember. And then maybe you need to copy something in here. So what we did in here, we copied what? We copied ESI, and ESI is pointing at A, so we have taken A. Okay? So when we do that, when we say push, we decrement and we get A. That's push, I'm sorry. And then we said increment ESI. When we say increment ESI, we are here, now we are going to B. That is the dot data memory. So you are moving from the dot data memory to the stack now. And then later we're gonna move it from the stack to the dot data. We will see that. So we're gonna do this. Then the second time we're gonna say this is, let's say 10 or 11 names. Then we subtract 1 from 11. It's gonna be 10. That's not a 0. We're gonna go back to where? To L1. So now we are pointing at B, right? So we're gonna get this B and then we're gonna push it where? Here. So we have to subtract 1 first, and then now we have what? B. So we're gonna go like this. We're gonna do this again for the R and so on and so forth. It's gonna grow in this way until we get to the end, okay? So once we're done, once we get to the end, then we are out. All right, so what we're gonna do right here, remember, we said move the name size back to ECX. Didn't we do that already here? Why do you wanna do it? Because this loop already exhausted ECX. When you get outside of this loop, ECX is no longer the length, 11 or whatever the length of that string. So it's 0 when you get out of here. So you better get it to the ECX. Get the original value back to ECX. So that's what we're gonna do in here. We're gonna move the value to ECX, okay? And then we assign 0 to ESI. Why? Because we incremented ESI. By the end we finish, the ESI is not gonna be no longer 0, it's gonna be whatever the value we have right here, right? So we get these back in here, and then now we're saying pop. So when we say pop, at the end, the top of the stack is gonna be what? Here, somewhere in the stack, the last thing, and here is gonna be what? N. That is the last thing, right? Okay, so you're gonna get this, this pop, you get this N to EAX. And now you're reading, because since this is just a byte, because you don't need to read those, you just wanna read whatever you have in the bottom. In our case, is gonna be N. So we're gonna get that in and we assign it to the name ESI. So this is now, is no longer A, is gonna be N. So that's what I have right here. It's gonna be N. And then the next one is gonna be what? It's gonna be L, and then it's gonna be O. So we are going back to here and we're gonna overwrite everything in here. So that's what this pop is gonna do, okay? It's gonna take the value from the top of the stack, assign it to EAX, and then go to the AL, which is the first byte, because the others are nothing but extension. We don't need them. Take the AL, assign it here, is gonna override. So this N is gonna override this A, and this L is gonna override this B, and this O is gonna override this R, and so on and so forth. So by the end, if we're gonna look at this, you're gonna have this string. Okay, so that's another way to use the stack to solve problems similar to this, okay? And then we have some another related instructions. We're gonna look at them as well. So these are very important instructions. So this instruction we call push and pop, FD. So these are, they're gonna push E flag register. So if you wanna push the entire E flag register, right? The E flag register is what? 0 to 31, right? So like 0 flag, carry flag, and so on and so forth. So if you said, I'm doing a specific operation, and I know, let's say this is addition, I'm afraid that the subtraction is gonna change the status. I want to keep the status for some reason. So if the state of the program at a particular operation is important, you can push the entire register, E flag register, into the stack using this instruction. And once you do the subtraction here, and you want the state of the registers to be back where it was when you did the addition, you just need to use the pop. Okay? There are situations when you need to push the entire general purpose register, all of them, EAX, ECX, and so on and so forth. You can use push 80. Or you can use what? Pop 80. If you push all of them, and then you want to save the values in there for some reason. All right? So these are very important. So basic idea right here is something that we're going to look at is how to define and use a procedure. So we're just going to look at how to define, and then I know I've been covering a lot. I will stop right there. Okay? So we're going to go into a procedure and assembly language and how to really define a one. That's straightforward. It's like the main, right? You have a proc. The only difference here, you have what? A must-have return. So you have the name first, and then the proc, that's the keyword. So if I want to say add one, I would say proc. And then whatever I have, every function must has a return. You must have a return instruction. This is an instruction, okay? And then now you want to end it, you're just going to say add one, and then you're going to say end what? Procedure. So this is similar to this. The only thing that you have in here that it must have a return. Okay? So we will see later why that is the case. Okay, so you assign it a name, right? And you declare the procedure, and you end it with this, and you give it a name like the sample right here, okay? And you need to have a return. And we're gonna talk about why the return is important, right? Because if you have a function right here, one, and function one calls function 2, 5, and 6, and function one itself has a return. And you notice that, right, if you've done any kind of programming. So when you go to function 2, and function 2, you have A and B, right? And in function 2, somewhere you have to have the return, right? So we need the return. Why we need the return? This is going to get us back to here. Okay, so return is a very interesting instruction. It's a large program. We're going to break it down into pieces so you'll understand how a method returns a control to another method using the stack. So you'll see the importance of the stack. Okay, I'm sorry. So this is like best way to write a procedure or a function. You should apply this to everything, not only in assembly, but in any language. Really have the description, what your method or function receives, what it returns, and what it requires. So this is documentation type of. Okay, so in this case, we have this documentation describe what this function does, because it's hard to just look at it without this part in here, okay? If this part is really not there, it's gonna be really hard to guess. Of course, if you spend some time, you will know it, but this is more descriptive. So in this function, we just have the name, sum of, and then we have two instructions in here, and we have the return, and then that is the end of the name, okay? So remember these like three main things. The name, you have to have it, but these are fixed all the time. But the name, you can change it. The instruction here, it depends on the problem you're solving, okay? So I will just motivate you for call and return. So when we talked about here in this part, let me see, I think in the one before. So when I talk about this method, so here you have call, right? And then you're gonna go to F2, we will see how call works and how call uses the stack, okay? And again, when we say return, how the return actually works, and again, with the help of the stack. So what registers are involved and how the stack is being used to accomplish this. This is something that we're gonna cover, but I will give you some time to digest those information. And then the real business, guys, is gonna start from here, okay? So I cannot emphasize how important this part is, okay? So this is very, very important. All right, so we're gonna cover this in the next class, and hopefully I will get the opportunity to learn how to use Visual Studio and capture because that's a challenge for me. Right? It has been a challenge for me to, I can run the virtual machine, I can see the virtual machine box, but it's been a little bit hard to see whatever the virtual machine is running, but I will try to figure it out. Hopefully if I succeeded, I will show you, at least share with you how how push and pop works, and then we're gonna play with the return and call, all right? So for now, I would like to thank you for your time, and then see you in the next lecture, guys. Thank you very much.